Hello everyone, welcome to the OneClass channel. My name is Millan, and I'm a software engineering student at Carleton University in Ottawa, Canada. Today, I will be going over some commonly asked physics questions at both the high school and university or college levels. If you're interested in getting help with your homework, or if you're interested in getting some tutoring, check out the links in the description below. Cool, so we got a fun time full of physics ahead of us. I'm going to switch my screen ASAP fast. And we can get this physics experience started. Okay? Cool. So, let's take a look at the first question that we got on the menu today. And it is presenting the following situation, okay? So it looks like we have a person that's asking us, please correct me, what did I do wrong in this quiz? My teacher only gave me a grade but didn't mark what was right or wrong. And, we should basically just trying to correct this, okay? So if we zoom into the page a little bit here, let's see if I can actually bring this over. Even better, okay? So we have the actual picture just ready for action here. So we're presented with the following situation. Okay, so we are given uniform acceleration. Okay, so I'm gonna just take note of that. Star uniform acceleration. That means our acceleration never changing, which is pretty important because that's going to allow us to use kinematic equation. Kinematics equations. Now, kinematics equations are awesome because they, they're fairly simple to use and they can always tell us the right answer of the things that we need for constant acceleration. But as soon as that acceleration changes, we're kind of out of luck and we can't use our kinematics anymore, but we're not going to worry about that right now, okay? So, given uniform acceleration, an object has an initial velocity of 15 meters per second towards the east. And after 20 seconds, it has a velocity of 40 meters per second to the west. Thinking to our compass, we know that our compass is looks a little bit something like this. Never eat shredded wheat. A great way to remember it. So initially, our velocity, let's call that u for initial velocity. That's pretty common. Sometimes you might also see it as like vi for initial velocity. So our initial velocity is 15 meters per second towards the east. So going from left towards right if we're looking at a compass. And our final velocity after 20 seconds, okay, that's another thing that we're going to need to keep in mind. Our time here, 20 seconds. And after 20 seconds, it has a final velocity of 40 meters per second west, going the complete opposite direction. So for final velocity, it's fairly common for people to use v, and we got to put an arrow on top of it. Remember, it's a vector and it's going the opposite direction. So this is 40 meters per second. That's pretty fast. And this is west. It's good to surround it by square brackets just to specify that it's a direction. Okay, so the first question on the menu today, or the first thing it's asking, is the average velocity here. Okay, so keep in mind that our velocity, initially, we're going towards the east, and then over some time, we pretty much made a whole U-turn and, switched our directions. Okay, so the first thing that we're going to need to do is we want to define a direction. Okay, it seems like you've done your math well for the person asking this, but I'm going to write on top of you just to show like why it's completely right and why you are a physics rock star. Okay, so define a direction. Let's say east is positive. That would mean that west has to be negative. There's nothing wrong about going towards the west. It's just like how we have to set up our things. Okay, so our u, another way that we can write our u is towards the east, so that's going to be positive 15. And our v, since it's going towards the west, is going to be negative. Okay, so I'm just putting these signs here. Now to find the average velocity, Our average velocity is the sum of our velocities, because we have constant acceleration, uniform acceleration. So that means we just add the initial velocity plus the final velocity and divide it by the time. Oh, not by the time, that would be the acceleration. We're going to divide it by 2. And this is average velocity. Okay, so that's exactly what we're going to do. So our initial velocity is 15, positive 15, because remember, towards the east, we said is going to be positive. So plus 15 meters per second plus the final velocity. Now we know our final velocity is going to be a negative number because we're going towards the west, and we said towards the east is positive. So we got to do negative 40 meters per second and divide that whole thing by 2. Okay, so I know that's going to be 25 over 2, negative 25 over 2. That negative is extremely important. Meters per second over 2, and that translates to negative 12.5 meters per second. And it might be even better to even write that this is towards west. Okay, so this is our average velocity, and that makes sense because our final is going faster west than we were initially going east, so our average should be towards the west. Okay, so yeah, that's cool. So under here we had negative 25 over 2. It's just better to write that as like an actual, or to calculate that through to negative 12.5. Okay, awesome. So the next part of the question is asking, what's the change in velocity? So the change in velocity, as is written here, is simply is represented by delta V. The delta is the triangle looking thing to the left side of the V. That's a Greek letter to specify final minus initial. This is not just for velocities, but for distance as well, for time. This will always, that delta operator, it means difference, final minus initial. Don't forget it. Keep that in the brain forever. You're gonna need it forever. Okay, so we're gonna do the change of velocity is like well, that's just our final velocity minus our initial velocity. So we used v and u, so we're going to continue to use that convention here, v minus u, both as vectors, but we're going to convert them to follow our same east-west positive minus convention. So our final velocity is towards the west. We said west is negative, so that's got to be negative 40 meters per second. And then we're going to minus our initial. Our initial was 15 meters per second towards the east. We know our east is the positive direction, so we're going to subtract a positive number from here. Plus 15 meters per second. And, well, compute that math. 40 minus 15, or negative 40 minus 15, negative 55 meters per second, which is precisely what you got here. So a big high five on that. Good job. Negative 55 meters per second. Awesome. Cool. Okay, so that addresses the second part of the question. Now we can move on to the third part of the question, the acceleration. Now the acceleration is, by definition, acceleration is the change in velocity with respect to time. How much does your velocity change over time? That's what acceleration defines. And we know that the acceleration is constant. That was like one of the first little clauses of this situation that was presented to us. So to calculate the acceleration, we need to find our change in velocity divided by our change in time. That's the definition of acceleration. And acceleration is a vector. Do not forget that acceleration is a vector. If you forget that, you're going to be in trouble. Big trouble. Okay, so it's going to be the change in velocity divided by the change in time. We know that our change in velocity, well, we just calculated that in our previous question. That's negative 55 meters per second. That's where it came from. And divided by our time, how long did it take for us to change from our initial velocity to our final velocity? The question told us 20 seconds. Okay, so we're going to divide that by 20 seconds. And if you look at the unit, The unit is going to be meters per second, which is equivalent as saying meters per second squared. Let me just erase that. So meters per second squared. Essentially what that means is our meters per second changes every second by this amount. Okay, so then we're going to do a quick calculation. 55 divided by 20. Now, I am not the sharpest tool in the shed, so I can't do that in the mind instantly, but that's okay. That's why we got calculators. And I got negative 2.75 meters per second squared. And negative, well, that for the same reason we have going towards the west as our negative direction. So even better, it would be to say like the acceleration as a vector is 2.75 meters per second squared in towards the west. Okay, that would be the vector way of saying this. And for this as well, we want to specify that this is going west. Okay, if like the question asker was mentioning that the teacher gave a mark but didn't say was right or wrong. If there were things wrong about this, I think what could have went wrong is that the directions of the vectors maybe were not specified extremely clearly. Also, you want to convert your answers into like decimals. In general, decimals are generally preferred as a final answer in physics. Math is a little bit of a different story, but in physics, you're gonna, and especially engineering, because that's physics and engineering are tightly related, like siblings. You're gonna want decimal type answers. Okay, and yeah, so now we can move on to the last little section of this question, which is asking us for the displacement. Basically, how much did we move? What distance did we cover for this to be possible, for us to change our velocity from 15 west to go to 15 east to go to 40 west, all in meters per second. Okay, so for this, definitely from what we got here, it's a great start. We want to start with our kinematics equations. Okay, so the kinematic equation that we want to keep in mind here is that our change in position, our x, or our delta x, which is displacement, we could also write this as d, is equal to our initial velocity times time. Whoops, not that one. So our ut, and we will add plus 1/2 at squared to that. Squared. Okay, so this comes from kinematics. Kinematics equation. Okay, so to solve for d, well, d is already isolated, so we just have to sub in our numbers, and then we can be very happy that we found the displacement. Okay, so d is going to be equal to, our u value is positive 15. We're going to still follow our east-west, east positive, west negative convention. So our u is positive 15 meters per second, multiplied by our time, that's 20 seconds, plus 1/2 multiplied by our acceleration. In the previous question, we calculated it to be negative. That's very important. It's negative. Negative 2.75 meters per second squared, multiplied by t squared. And t is 20 seconds, but we got to square that. Okay, so 20 times 20, 400. Okay, now I'm going to send this all through my calculator to figure out what the numerical answer to this calculation is. 15 times 20 plus 0.5, that's the same as divided by 2, times negative 2.75 times 20 squared. And my result for this is d is equal to negative 250 meters essentially what this means is our final displacement is 250 meters west of where we started from. Okay, so if we started here, we were going like this, and then eventually our acceleration took over, and this is our end point right here. Okay, kind of like we made a little U-turn, and that is our position. And we calculated the same thing here. That's awesome. Or numerically, that's awesome, but we're looking for vectors here. So to say answers are all correct, yes, but to be held to higher physics standards that are very common, especially with what physics leads to into like engineering as well as more general science, we need to incorporate the vector quantities. Okay, so the above solutions are numerically good. However, the given info is with vectors, so the answers would be better as vectors as well. Note a direction, not a direction, note a direction instead of a sign for these situations. Cool. Okay, so here we have the next question on the menu today. It is asking us, or is presenting the following situation. Okay, we are exploring a cave, a spelunker. I guess that's like it's a cave explorer. A spelunker starts at the entrance and moves the following distances. Okay, so let's actually like kind of draw this out as we read through this, because at the end we're going to try to find the resultant displacement, how many meters of displacement, and in what direction. Okay, so let's say this is our starting point right here, and the first step is we're going to go 75 meters north. Okay, so I'm going to try to be on the grid and be fairly consistent with my distances. Okay, so 75 meters north is our first step, and then 275 meters towards the east. Okay, it's going to be very difficult to draw to scale now. 275 meters east. Not 27, 275. Okay, I'm actually going to need to move this whole thing because I didn't realize how much east we were going. Maybe down to here. Okay, cool. Back to action. The next step is 175 meters at an angle 30 degrees north of east. So we're going to go directly east, but just slightly north of that by 30 degrees. Let's get our pen here. So something like this. Okay, comes 30 degrees north of east, and that was 125 meters. 175 meters, my bad. And our last little step of the journey, 150 meters directly south. It's going down for real. Something like this. Okay, so our first thing that we're going to try to find here in this situation, to draw this more precisely, is like this. We are looking for this little angle, or this vector right here. This is our target. We are looking for its magnitude and as well as its angle. Now, from the way that I drew this, it looks like target is going to be like southeast, but that could just be my drawing errors, right? So keep in mind that these are not necessarily to scale. It could also be pointing this way as well, depending on you know how to scale your drawing is. But this is like the general gist of it. Essentially what we're trying to do is we have a vector situation right here, right? So we see that the red target arrow is the same as this like head to tail chain of all the steps that were described in the question. Essentially what we're going to try to do is treat all of these individual steps in the journey as individual vectors, add them together, and then that's going to be the target. Okay, so how we're going to do that, let's call this A, let's call this B, let's call this one C, and let's call this one D. Okay, fairly straightforward, and they're all vector values. So if we wanted to, maybe let's just call this T for target. We know that the value T as a vector, that's going to be the vector sum of A plus B plus C plus D, like this. Plus C plus D. Okay, so conveniently, a lot of these vectors are in one, are like perfectly in the north-south or east-west direction. But C, this C vector is, you know, it's northeast, so it's going to be a little bit more difficult to deal with. That means what we're going to need to do here is we need to convert all vectors into Cartesian form. Essentially what Cartesian form is like I and j with the unit vectors. These will be our unit vectors. And I is going to correspond to east being positive for I, and j is going to correspond to north being positive. Okay, so instead of using like northeast, south, and west, maybe you might be more familiar with a Cartesian system like this of x and y. You know, we're still have two perpendicular directions, but it's just like a different way of representing them. Yeah, so just imagine like east and north as our stuff like this, and how we're going to make these vectors with I and j components in Cartesian form is actually fairly straightforward. Okay, so let's take a look at our first step, which is A. A is just 75 meters to the north. It does not have any east-west movement, so it's purely going to be a j vector. It's only going to have one term in it. Okay, so how much it's going north, so it's going to be a positive j term, and 75 meters is how much it is. So to write this out, A as a vector is equal to positive, because we're going north, 75 in the j direction meters. Okay, now what about B? B is kind of similar. We're only going east-west, no north to south movement. So there's no j term associated with the B vector. It's just going to be I. So if we wanted to write out our B vector, we are going to be going straight towards the east, and east is our positive I direction. So this will be a positive term. Our magnitude, 275 meters in the I direction, and meters. Okay, fairly straightforward. Now C is going to be a little bit spicier, because you can see C has both some horizontal movement, like it's moving horizontally by this much, and it's moving vertically by this much. Okay, so we need to pretty much, what's going on here in green is we're going to like redraw C as like Cx component and Cy component. Okay, because so essentially what this means is that C as a vector is going to be Cx component in the I direction plus Cy component in the j direction. Okay, so how do we find Cx and Cy? they are really just going to be these lengths right here. And if you look closely, this looks like a right angle triangle. With the right angle being here. What do we know about right angle triangles? If we know the hypotenuse, that's the 175, that's our hypotenuse, and the angle here, does that ring any bells? SOHCAHTOA tell me? SOHCAHTOA? Does that sound familiar? It sounds familiar to me. So that's essentially exactly what we're going to be doing here, is our CX component is just going to be it's adjacent to the angle, so that's going to be cos 30, 175 times 175 meters. And CY, well, that's going to be similar, but on the other side, it's going to be sine, hypotenuse and opposite, SOA of the SOHCAHTOA. So sine 30 degrees, 175 meters. Okay, so these are the individual x and y components of C, just using the power of trigonometry. Okay, so let's write out C as a complete vector here. Okay, so we know that the x component is going to be cos 30 times 175. Let's actually get that as a calculation ASAP fast. My cosine is not that quickly done in my mind, so I'm going to use the calculator for that. And I got 151.55, and this is in the east direction, so it's going to be positive. So positive 151.55 in the I direction, and in the J direction it's also going to be positive, and it's going to be sine 30 times 175. So 175 times 130, that is 87.5. That is positive, plus 87.5 in the J. And with these multi-term vectors like this, you can surround them by brackets and put the unit outside. It means the same thing, and you don't need to write like meters on every single term. It's not really a big deal when you're in 2 dimensions, but these vector concepts will still be the same if you go to like 3 dimensions or even 4 dimensions if you go into like theoretical physics with like the curvature of space-time and all that. You don't need to worry about that right now, but it's just a good thing to keep in mind. Okay, and our last vector is D, our wildly not to scale D right here, but it's going straight down, so that's fairly easy. Going straight down, that's purely in the J direction, and because north is positive and is going straight down, it's got to be negative J direction. Okay, so it's going to be negative 150 J for D. If you forget that negative, big trouble. Negative 150 J meters. Okay, now we just got to put them back into here, and we can get our T value. Okay, so A is plus 75J, and I'll write meters all at the end. So this corresponds to A plus our B vector, which is 275I. Okay, that's our B, plus our C vector, which is 151.55I plus 87.5J. That's our C, and our D is going to be negative 150 in the J direction. Okay, so essentially, to do this math, if you're not already familiar with it, we're going to try to combine all of our terms that are I and all of our terms that are J. Okay, so underlined in red are our I terms, and underlined in green, those are the J terms. Okay, so the result of T, the I component is going to be the red terms together. So that's going to be 275 plus 151.55. Okay, so overall, we've gone 426. 426.55I. And then for our J, we got to put all the green terms together. So we got 75, that's a positive, plus 87.5, also a positive. But, oh, don't forget that negative, minus 150. Okay, so that is, as a result, positive 12.5 J. Looks reasonable to me, and that is all in meters. Okay, now does this make sense? It means that we went 426 meters towards the east, very far east, and barely any, and just like 12 meters north. So my diagram is a little bit wrong. I think that's because D I drew a little bit too long, so we would actually expect our target to be pointing upwards. So we would actually expect it to look something like this. That's what it would look like, okay? So it's asking us how many meters this is. So essentially what this means is we need to find the magnitude of this vector. Because what's really being represented here is we know that this is going to be 426.55 I, and we know that this right here, that's going to be 12.5 J. Okay, now if you look closely, another one of those right angle situations, right angle triangle situations, and we know the two side lengths, and we're trying to find the hypotenuse. Do we know how to deal with this? Yes. The power of Pythagoras Theorem. Okay, so to write t as a magnitude, it's typically written with a absolute value like this. Sometimes you'll even see double absolute value, and that's just to like be double sure that this does not get confused. It's just to say the magnitude, and you calculate this with a Pythagoras Theorem type of operation. Okay, so we have our I term, 426.55, and we're going to square that and add it to 12.5 squared, all under the root. Okay, we don't really need to worry about plus minus on this one. So we just got to take this calculation too fast, ASAP fast. Okay, 426.55, square that, add 12.5, square that. Take the result of that and put it in the square root, and my result is 426.73 meters, and that is a reasonable answer, and that's because because the horizontal, the east, is so much larger than the north-south direction, we would expect that our t is going to be very, very close to our I, just because I is so much larger than j. So that makes reasonable sense. Okay, so this is our total meters away. That would be yeah, we got the same calculation here. That's awesome. Okay, now to find the angle, essentially we're looking for this little angle right there. That's that theta angle. And another one of these right angle triangle situations we could think back to SOHCAHTOA. We know that our tan is related to the angle as well as the opposite and adjacent. We know tan theta is equal to op over adjacent. So if we were to isolate theta, we just got to do tan inverse of the opposite divided by adjacent. So the opposite in this case, 12.5. That's the j component, the vertical or north-south component. Okay, so 12.5 and divided by adjacent 426.55. Send that through the inverse tan, also known as arctan, and let's see what that is. So 12.5 divide 426.55. The result of this calculation I got is theta is equal to 1.68 degrees, and is going to be this way. Okay, so just counterclockwise of a horizontal towards the right angle. Okay, and it's good to like draw a little symbol like this. This is what I got right here to kind of specify which direction or where this angle is respect to. Okay, so yeah, that would address all parts of this question. And how much are we north of east? That's essentially what this diagram is saying, or this little image is saying, 1.68 degrees. Okay, very small angle, but still noticeable. Just a little rounding discrepancy there, but otherwise this is a perfectly reasonable solution. That's awesome. Okay, big high five. Here, above solution is good. Good job, high five. Ain't that fun? Okay, so here we have the next question on the menu today, and is presenting the situation where we have a boat anchored at a river bank. Okay, this is gonna be what I interpret that as meaning, because this question is not super visual, but we can make it work. Okay, so here we have a boat right here. Let's just call that boat. And it's anchored at the riverbank, okay? Due to strong winds, it would move on a quiet lake with a constant velocity of 10 meters per second in a direction negative 30 degrees with respect to the horizontal. Okay, so essentially what that means is that we have a wind speed. Let's call that VW for wind. This has a magnitude of 10 meters per second. And this angle is 30 degrees. 30 degrees, I guess clockwise, because clockwise is typically mentioned as the negative direction of a horizontal. Okay, so this is our wind speed, and our another speed that we have is the river water speed is 15 meters in 15 meters in the positive x direction. So if we define our xy axis like this, that would mean our v water. Okay, maybe VW does not work great for v wind, but let's just call this VH2O, and that's going to be 15 meters per second. Okay, so these two right here, maybe I'll highlight a circle around them. These are environment speeds. Okay, cool. Now the ship wants to cross the river with a velocity of okay, so that's the we need to calculate the velocity that the boat needs to go in order to pass like directly across in the y direction like this. Maybe I'll draw that path in red. And we know that this distance is our destination. D for destination. And we know that that is 300 meters. And we need to get there in 1 minute. Okay, so the boat needs a velocity. So VD, this is our velocity to our destination. This will be 300 meters divided by 60 seconds, because it's 1 minute. And this will be in the y direction. Okay, so that's just J for direction. Positive J, because we're going up. I know it doesn't oh, it says from A to B. Okay, so we're good on that. And 300 divided by 60, that's I think that's 5 meters per second. Just to be 1000% sure. Yeah, okay, so this is what we need. 5 meters per second in the J direction. This is our target velocity. So we need to decide what the boat's velocity is, so that the velocity of the boat plus the environment speeds are going to be equal to our velocity to get directly to our destination. Okay. So to write this out mathematically, we're going to need to do VD Our effective velocity as a result of all our boat, as well as the water that we're in, as well as the wind, is going to be equal to, well, all those things individually. We're going to have VB for boat plus velocity of the wind, W, and plus the velocity of H2O for the water. And, well, we're given some of these terms directly, and we're trying to solve for VB. So just like typical algebra, we can take the VW, the wind speed, as well as the water speed, and bring it to the left side of the equation, isolating VB on the right side. But we got to make them negative. So V wind minus V H2O for water. Beautiful. Now that is the V of the boat that we are trying to solve for. Okay, so we need to put in our vector values for here, and then we'll just calculate for VB, and then we will be extremely happy that we found the solution. Okay, so the first thing that we need to consider is VW. This is 10 meters per second, but it is 30 degrees below, or negative 30 degrees with respect to the horizontal. Okay, so you know that if VW looks like this, and this is our horizontal, that's 30 degrees, and this is VW, and that has a magnitude of 10 meters per second. We know that we could break this down into its x and y components like this. Okay, and those two green vectors added together would be the same as VW. And to find these, hey, this actually looks very similar to a right angle triangle. Maybe with the power of trigonometry and SOHCAHTOA, we could find out the VWX and the VWY of these components. Okay, so we could write this as, well, VWX, we know that that is adjacent to the angle, and that is in the positive x direction, so that's going to be positive sine 30 times 10. Not sine, cos 30 for adjacent. Be very careful with those, and that's going to be positive times 10 in the I direction, my bad. And then in the j direction, we're going negative, so we got to have a negative term out here. And if we use cos for one, we're going to probably use sine for the other. And you can double check that. I know for a fact that's got to be right. Times 10 in the j direction. Okay, cool. So we can math this out real fast. So cos 30 times 10. Let's ask the calculator, what is that? That's 8.66 in the I direction minus 5 in the j direction. A good thing to keep in mind is that sine 30 is 0.5, same as divide by 2. Okay, so here we have our VW, and VH2O we are given, and VD, our actual final velocity, is also given, so we can just sub those in. Okay, so VD, we had 5 meters per second J, positive 5 meters per second J. So 5J, that corresponds to VD minus, now if you mess up these minuses, big trouble. So we have to be extremely careful here. So now we have to do minus VW. So we're going to put VW in the brackets, but that minus in front, real important. Don't forget that. 8.66 I minus 5J. And this will be VW for the wind. We also got to do another subtraction. That's going to be the velocity of the water. How fast is the water moving? And that's going to be 15 in the positive I direction. And we're going to keep that in the brackets. Positive 15 I. But don't forget about that negative out front. Okay, so that's VH2O. And the result of that calculation is going to be the velocity that the boat needs to have. Okay, cool. So let's continue doing the mathematic magic with this. Oops. Okay, so to multiply out these negatives, we'll have something like this. So 5j minus 8.66i plus 5j minus 15j. Oh, that's not 15j, 15i. My bad. That would have been a catastrophic error. Okay, so velocity of the boat, and let's put all of our I terms together. We have so 8.66 and 15 together make negative 23.66 I plus 10 j is equal to the velocity that the boat will need to have to go to follow that path. Now it's going to need the speed and direction. So this is the Cartesian form. We want to get the magnitude and angle of this for our speed and direction. So our magnitude, essentially what this means is here we have 10j, and this is wildly not to scale, so don't believe that this is actually what it looks like. It's just like kind of similar. So negative 23.66 I, and this is right here VB. Given that it's a right angle triangle, here we will have to do Pythagoras Theorem to get the magnitude of VB. And to write that in a mathematics sense, we have a situation like this. So these double absolute values is to represent the magnitude of the vector. We're going to put it under the root, and we will Pythagoras this theorem. 23.66, square that, plus 10, square that, all under the root. Okay, let's ask my favorite little calculator. What in the world is that? Okay, let's put them under the root. 23.66, square that, plus 10, square that, all under the root. Our velocity that we'll need to have is 25.69 meters per second, and that's it. Okay, but we also need to find the direction, and pretty much what that means is we need to find this angle right here. And so, you know, another right angle situation, we just got to use tangent, right? We have the opposite and the adjacent. We know that our angle is the inverse tan of op over adjacent. In this case, our opposite is 23.6. We only need to really worry about the magnitude in this case, and how we're going to contextualize and give a sign to this angle. You know, we want to go out visually. So just the magnitude is going to be 23.66 divided by 10. Nice and straightforward. Okay, so let's figure out what that is. 23.66 divisé par 10 en français, and we get our angle is going to be 67 degrees counterclockwise from the vertical. Okay, so our final VB vector is going to look a little something like this. This angle, 67 degrees, and the magnitude is 25.69 meters per second. Okay, this is what our velocity of our boat will need to be. Which kind of makes sense. Like, we have wind going this way. Wind, maybe let's draw that as blue. Wind, we have water going this way. So it makes sense that we will need to go like against the wind and the water, and we need to like counteract their velocities in order for our boat to travel directly across the stream. Okay, so yeah, this would address this question. I thought that was a really fun time, so let's mark this question as good and keep it moving. Awesome. So there is no above solution. Velocity of boat that a boat should have is 0.69 meters per second at an angle 67 degrees counterclockwise from vertical up. Cool. Okay, so here we have the next question on the menu today, and it is presenting the situation where we have a girl delivering newspaper covers, and her route is 3 blocks west, 4 blocks north, 6 blocks east, and we're trying to find what is her resultant displacement and the total distance that she has traveled. Okay, so let's actually draw a diagram of this path that our newspaper deliverer is following. Okay, so right here, let's call this our start point right here. Okay, so the first step in our journey is 3 blocks to the west. So west is towards the left. So that's 1 block, 2 blocks, 3 blocks. Arrow going this way. Okay, the next step in our journey, 4 blocks north. 3, 4. 4 blocks north, and our next step is 6 blocks east. 1, 2, 3, 4, 5, 6 blocks east. Okay, yeah, and this is our weather girl's path. I mean, not weather girl, newspaper girl's path. Okay, so the first part of the question is, what is her resultant displacement? And to represent that on the graph, we just have this situation. Okay, maybe in red. The shortest distance between her start and her arrival point, this is our displacement d. And that's a vector. Okay, that's real important. It's a vector. So we're going to need a magnitude and a direction. Okay, so let's think about how much she actually traveled, right? Because she went west initially, but she undid some of her west movement by going 6 blocks east. So effectively, her east-west position is that she is 3 to the east of where she started. And our diagram perfectly lines up with that. So our x component of our displacement is 3 blocks. And our vertical component of it is, well, she traveled 4 blocks north and never traveled south. So we're just going to have 4 blocks north as our y component. dy is 4 blocks and in the j direction, and here in the I direction, just so that we're familiar with this. This is our x or our I direction, and this is our y or our j direction. You might not be familiar with this now, but you will definitely see it a lot in the future of your mathematic journey. Okay, so if we know that, hey, this kind of looks like a right angle triangle, doesn't it, right? If we take a look like that and a look like this, this kind of looks like a right angle triangle. And we're looking for the distance of this hypotenuse here. Do we know of an easy way to find the hypotenuse of a right angle triangle? I sure do. I know of my good friend Pythagoras Theorem. We know that the magnitude of D, kind of represented with like these absolute value bars, the magnitude of D is, we're going to find the Pythagoras theorem of the x component and the y component together, right? Because those are the non-hypotenuse sides of our right angle triangle. So to do that, we're going to put it under the root 3 squared plus 4 squared. And I know the result of this is the square root of 25, and that is 5. These 3, 4, 5 triangle is very common. You're most likely going to see it a decent amount, so you know, it's good to stay familiar with this. And our units are important, is going to be blocks. Now that's one step of our displacement journey, but displacement is a vector. We have the magnitude, we also need the direction, and our direction is pretty much can be represented by that angle right there. How would we find that angle? I'm glad you asked. We can just use the power of an inverse tangent, right? We know that the relationship for a right angle triangle between the angle and its opposite and adjacent is tangent. So we know that angle has to be the inverse tan, the arctan, also known as, of the opposite over adjacent. So in this case, dy over dx. So our inverse tan of 4 over 3 is going to give us an angle that my calculator will tell me, because it's very difficult to do these type of maths in your noggin, but that's why we made calculators. And I got 53.13 degrees, and this is counterclockwise with respect to the positive x-axis that we defined. And to kind of represent what that means, you can draw a little drawing like this just to show that this is like the direction of the angle. Okay, so her displacement is 5 blocks, 53.13 north of east. You could also write this as this, north of east. Okay, that's another way that we could represent this, and that would address the first part of the question. What is the resultant displacement? That's beautiful. Okay, the second part of the question, much easier, is what is the total distance that she traveled? And this is going to be a lot easier, so we just have to look at every individual step of the journey, see how much distance was covered in that individual step, and then add them up. So our first step is 3, our second step is 4, and our third step is 6. So our distance traveled this is just going to be 3 plus 4 plus 6 blocks, because that's the unit for distance that we're using. Sometimes we use meters. I guess here is where we're going to be using blocks. And quick math, 13, lucky number. 13 blocks. That is how much our newspaper deliverer traveled. And that's the calculation here. That's awesome. Oh. Oops. Okay. So here we have the next question on the menu today, and it is presenting us with the situation that we are driving to the grocery store at 24 meters per second. We are 130 meters away from the intersection when the traffic light suddenly turns red. It takes half a second for us to realize that it's red and push the brakes. And once we hit the brakes, we are slowing down with a constant acceleration. Okay, that is an important fact here, is constant acceleration. Deceleration in this case, so you can actually kind of think of it as a negative acceleration. Constant A for acceleration. This means kinematics, or that we can use kinematics. Kinematics is one of the tools that we can use. Big happy face because kinematics equations are fairly straightforward once you get some practice with them. Okay, so let's actually draw a diagram for this situation. So here we have our car going super fast. Vroom, vroom. And we know that our velocity initially is 24 meters per second. And let's call this u. Maybe not as a vector, because this is a one-dimensional thing, so we don't really need to use vectors, but you know, those of you who are thinking about it, respect. Okay, so we are 130 meters away from the intersection. Intersection. And this distance right here, 130 meters. Okay, so the first part of the question that we need to, another thing is that delay. Let's just call that TD for the delay of when it turns red and when we register. Oh yeah, that's red. Let me push the brakes. That time is 0.5 seconds. Just 1 to 1 0, 0.50 seconds. Okay, cool. So the first thing that we need to consider is that we are not going to be 130 meters away from the intersection when we start decelerating. We actually need to find out how far we'll be when we actually start to decelerate. So right here, let's call this dr, reaction distance. This is distance traveled while reacting. So this will really just be our velocity multiplied by the time delay that it takes for us to register this as a red light. And this will be our velocity, which is 24 meters per second, multiplied by 0.50 seconds. You can see that the seconds cancel out in the units, leaving us with 24 divided by 2. So that is 12 meters per, well, just meters, 12 meters. So effectively, our deceleration area distance, let's call that DD, is going to be 130 meters minus 12 meters, and that is 118 meters. 118 meters. Okay, so this is the real distance that we are able to decelerate in. Okay, so we know that at this point our initial velocity is still 24 meters per second, and we need our final velocity to be equal to 0 meters per second. Why? Because we're trying to stop, and when we're stopped we have 0 meters per second, and you definitely don't want to be moving at a red light. You'll be in trouble. You might get a ticket, or even worse, you might hit someone, and that is bad news for sure. Okay, so we are looking for the acceleration. We're looking for A. Well, not as a vector, because we got to think about this in 1D. What are you, A? We're trying to find you. Okay, so thinking back to our kinematics equations, we need a kinematic equation that is related to the initial and final velocities, the acceleration and distance, and the one that I'm thinking is that our final velocity, v squared, is equal to u squared plus 2 times acceleration times distance. Okay, this is the kinematics equation that we want to use, and to make this useful, we need to isolate A. And to do that, well, we will subtract both sides by u squared and divide both sides by 2d. So A is equal to v squared minus u squared divided by 2d. And then we just substitute in these numbers, and that will be all we need. Okay, so A, what's v squared? Well, that's 0 squared. Okay, nice. And minus u squared, which is 24 squared, over 2 times our distance, and that is the distance that we just calculated. That is how much distance we actually have to decelerate, 118 meters. Now, you can see that this is going to be a negative number because we have a negative divided by a positive. Ignore that 0. That can just be like whoop. And we would expect to have a negative number because we need to decelerate. If we had a positive a, that means we're accelerating, we're getting faster, and when we see a red light, that is like the exact opposite of what we're trying to do here. So we're going to expect a negative answer. So 24 squared. Keep in mind that negative is after the squaring happens. Divide by 2 times 118. My result for this is negative 2.44 meters per second squared. This is our acceleration. Put a box around it to make it feel important. Give it a highlight. And that's our acceleration. Beautiful. Did we come to a similar conclusion here? Beautiful. Okay, so the next part of our question is asking us how long does it take for us to stop after this light turns red? Okay, so essentially we're going to need to use another kinematics equation to figure this out, and one that relates with time, but the easiest one that I have in mind is V equals u plus at, the simplest equation, and we're trying to isolate for t for the second part of this question. So to isolate for t, we're going to have v minus u divide a is equal to, well, t. And let's sub in our numbers and figure out what the math of this works out to. So we know our final velocity, that's 0, minus our initial velocity, 24, all divided by our acceleration. We just found that to be 2.44 meters per second squared, and this will give us our time. And you see how we have a negative on the top and bottom that will cancel each other out and make it a positive, which is what we expect. We would expect a positive time value. So we have 24 divided by 2.44, and this takes 9.83 seconds. Okay, so that will be the time taken to slow it down. Okay, I hope we came to the same conclusion here. We came to a slightly different answer because they came to they use a different kinematics equation. The only discrepancies between these two answers is likely going to be due to a rounding error. So, both of these answers are legitimate because in physics we do have to accept a certain degree of variability between our final answers, and that is due to measurement errors and all that. But like this small 200 millisecond difference is not that significant, so these would both be considered reasonable right answers. But I think this way is a lot easier because if you use that other kinematics equation, you will need to use quadratic formula. So this will be a lot easier in my opinion. Okay, cool. So the above solution is good. Would be easier to solve for time using V equals U plus AT. Awesome. Okay, so here we have the next question on the menu today, and we have an electric circuit. Let me just draw this out a little bit larger so that we can see it better. Okay, so on the far left, we got 2 ohms. Let's call this RL for R left. Down here, we have a voltage source like this, plus minus. I prefer to draw my voltage sources like this, because when you get to capacitors, it's it can be uncomfortable to draw these line voltage sources. And that's V2 down here. And V2 corresponds to 3 volts. Cool. Up here, we got another voltage source that's like this, plus, minus. And here is V1. And this is a larger voltage of 14 volts. Okay, cool. Okay, here we have 4 ohms. Let's call this Rm for the middle resistor. And over here, because I know my camera is just right there, this will be 5 ohms. Let's call this Rr for the right side resistor. And here we have a plus minus. This will be the third voltage source, which has a voltage of 8 volts. Okay, so our question is we have to find the current going through all of these resistors. Okay, so essentially we're going to try to do a full circuit analysis of this. The method that I am about to use is a system called Nodal Analysis. I learned this in my electric circuits engineering courses. Okay, so Nodal Analysis. So for nodal analysis, the first thing that we're going to want to do is we want to identify all nodes in our circuit. Okay, so here we have 1. And a node is any part of the circuit that attaches to more than one element. Okay, so this node right here attaches to 2 different voltage sources and a resistor. Here is another node, another node, another node, and another node. Okay, so wherever you see multiple circuit elements connected to each other, that's a node. Now we want to set one of these nodes to be our reference node, and we're going to really just try to find the voltage of all of these nodes. Once we find all of the voltages, we'll be able to find all of the currents. Okay, so we have 5 nodes in total. Now let's give them names. Okay, so let's call this let's give them like alphabetical names: A, B, C, D, E. Okay, so every node has an alphabetical name, and every node is going to have an associated voltage with it. Now we have one free pass to set one of these voltages to 0, and then everyone else is going to be with respect to 0. Okay, so I think maybe one of the easier ones that we could set to 0 is E right here. So to set it to 0 or to ground it, we can draw a symbol like this. Sometimes you also see it like a triangle, and sometimes you also see it like this. They all mean the same thing. That means the voltage is 0. Okay, so to write our voltages list, our node voltages list, we have VA, VB, VC, VD, and VE. We know that VE is going to be 0 volts. Okay, we only got 4 left to do, but they should be fairly easy from the diagram. So we know that in between node D and node E, we have a voltage source that has the D side 3 volts higher than the E side. Okay, so VD is just going to be 3 volts higher than E, and well, that's going to be 3 volts higher than 0. That's going to be 3 volts. Nice and straightforward. Okay, what about VC? That's going to be another fairly simple one, right? It's just going to be 8 volts higher than the voltage of E. E is 0. C has to be 8 above 0. 8, well, that's just 8. Now, A and B are not going to be as easy to calculate. We will need to do a little bit more work to figure out what they are, but that is nothing to be concerned about. And the reason why is because we know that the voltage difference between E and D is going to be 3 volts, but until we know the current in this RL, we're not going to be able to know like the difference in voltage between D and A. Okay, so we're going to need to calculate that. But some of the other tools that we might want to set up is we might want to assume some voltage directions. Okay, so maybe in red, let's just take a look at node B right here, and we're going to use what's here, the junction rule. So we know that all currents coming in is going to be equal to the currents going out. That makes sense. Currents can't spontaneously exist out of nowhere. Everything that comes in must be going out somewhere. Okay, so maybe if we just assume some directions, like here, let's call this IR. Let's call this one IL. And let's call this one IM for I middle. We know that the sum of outgoing currents is going to be equal to the sum of incoming currents. And this is the junction rule. Junction rule. And these are for currents. Current and current. Cool. So, who's incoming here? Incoming to B. IR is incoming. So, and IM and IL are outgoing. So that means IR is equal to IL plus IM. Equals IL plus IM. Now notice here that I wrote them on opposite sides. It is honestly, it doesn't even matter which direction you draw these arrows as long as you stay consistent with them. Okay, I could have easily drawn RM, IM, that is going upwards instead of downwards. I would just bring it to the other side of the equation, and in the end I would just maybe have a negative version of my IM calculation, but it would be the proper magnitude, and as long as my arrows indicate what's going on, everything will be cool. Okay, so now that we know that how these currents are related to each other, we want to use Ohm's law. Okay, that's another part of the thing that we're going to use. Ohm's law, we want to use that to help us find some of these currents. Okay, so we know that Ohm's law is related to this principle right here. Okay, Ohm's law. So if we have a resistance, if we have like V1 over here, in between V1 and V2, we have a resistance R and a current going through there. We know that Ohm's law technically is the change in voltage is equal to the current times the resistance. What that means is if I is going this way, V1, which is where we're starting, minus V2, our start minus our destination voltage, divided by R, is going to be equal to our current. Okay, so using this principle right here, we can apply this to these currents, and then we can get a relationship for this that is purely with respect to voltages and resistances. Okay, so this is what we want to do. So let's see how we can apply this to get the different I's here. So let's first start with IR. We know that, well, we're going to start at C, and we're going to traverse a resistor and get to B. So it's going to be VC minus VB divided by RR. So this will be IR. VC, where we're starting, minus where we're heading, VB, divided by RR. Okay, that's one of them, and we will sub these in eventually. And the next current that we want to find, let's say IM, we're going to start at VB, and we're going towards VE, so it's going to be VB minus E, broccoli minus asparagus. I know they sound similar, so I'm saying that to be super clear. Divided by the resistance of the middle is equal to the current in the middle. Okay, and our last one, well, we can't look at this voltage source directly, but we know that everywhere in this like left-hand side loop is going to be IL. Okay, so if we can actually just use this resistor right here, and we know that VA minus VD, that's where we're heading. A minus D is divided by RL is going to be IL. So desserts minus anchovies. Oops. VD minus VA. Whoops, opposite direction. That would be problematic. Alpha minus delta is equal to, divided by RL is IL. Okay, so that's the current that we have, IL. Now, using all of these equations along with that current junction law equation that we started with, we can assemble all of these together and then get a nice equation for that. So IR is going to be on the left side. VC, whoops, not plus. It's going to be minus VB. RR is equal to the other two added together. So VB minus VE. Oh, that kind of looks messy, just to make that super clear. Over RM plus VA minus VD over RL. Okay, so this is pretty cool and all. And if we sub in some numbers here, this will be even easier to deal with. So it's only A and B that we don't know what their numbers are. But the others we can sub in. So VC is 8 volts. VE is going to be 0 volts. And VD is 3 volts right here. Okay. Okay, the right resistor is 5 ohms. The middle resistor, 4 ohms. And the left resistor is 2 ohms. Now I know I'm going a little bit with a different strategy as we see on the left here, but we can always come to the same conclusion even if we take different strategies to get there. Okay, so let's sub in our numbers. We'll have 8 over 5 minus VB over 5. That's equal to VB over 4 minus 0 plus VA over 2 minus 3 over 2. Okay, so this is a little relationship. We have 2 variables, 2 unknowns, and 1 equation. We can't necessarily solve this perfectly right here, but we'll see in a minute that we actually can if we have a little bit more info. But let's reduce this down. So let's get all of our variables on the right side and all of our numbers on the left side. So here we'll have 8 over 5 plus 3 over 2 is equal to VA over 2 plus VB, and we'll factor out VB out of this term and this term right here. So it will be 1 over 5 plus 1 over 4. Okay, cool. So to simplify this a little bit more, 8 over 5 is 1.6 plus 1.5, that's 3.1, is equal to VA over 2, so that's 0.5 VA, plus 1/5 plus 1/4, that's 0.45, 0.45 VB. Okay, that's cool and all. We have 1 equation, 2 unknowns. Can't solve that yet, but if we look at our diagram, hey, do we see maybe a relationship between VA and VB? VA is 14 volts higher than VB, and that is should be fairly obvious from just looking at this voltage source between them. So this is VB plus 14. How about we sub that in to the equation down here? All right, we know that VA is going to be the same as VB plus 14 volts. So let's sub that into here. Okay, and that will give us 3.1 is equal to 0.5 times VB plus 14 plus 0.45 VB. Okay, expanding this all out, 3.1 is equal to 0.5 VB plus 7 plus 0.45 VB. And that will give us, if we isolate for VB, is equal to 3.1 minus 7 over 0.95. That is 3.1 negative 4.10. Yeah. Okay, so we have 4.10 volts for VB, and looking back to our diagram, we know that VB is it's got to be 14 higher than VA, right? So if we knowing VB is that, and VA is just 14 higher than that, we can easily calculate VA. 14 plus negative 4.10, and that will give us is that 9.9? I'll double check that on the calculator, because we can't always trust ourselves. Minus 4.10. Yep, 9.9 volts. Cool. So let's write all of these here. So now that we have all of our note voltages, this is negative 4.1 volts. This is equal to 9.9 volts. Now these negative voltages, they might be scary and they might make you feel like you've done something wrong, but don't worry about it. It is not that uncommon to see negative voltages, and yeah, just don't be too worried about them. Okay, so now that we know this, we can use these voltages in our current calculations, and that will give us exactly what we need. Okay, so for the current in the R branch, we just got to do the voltage at C, which is 8 volts. 8 volts minus the voltage of B, so minus 4.1 volts, all divided by the resistance of that branch, which is 5 ohms, equal to IR, and IR is going to be equal to 12.1 divide 5. My answer for that, 2.24, nope, 2.42 amperes. Okay, let's do a similar procedure for calculating the current in the middle branch. I wonder if it's going down. I feel like it's probably going down. It's going to be VB minus VE. Oh, that's VE is 0. So to write this properly, IM is going to be equal to negative 4.1 volts minus 0 over the resistance, so that's 4. So it's going to be negative 4.1 over 4. And that is 1.025, negative 1.025 amperes. So that just means that it is going the opposite direction as in the drawing. So in the drawing it's going down, but in reality it would be going upwards. That's interesting, but it makes sense given our calculations. And our last current, IL, is just going to be VA. We calculated that to be 9.9 minus VD, which was 3, all divided by that resistance, 2 ohms. So IL is going to be equal to 6.9 divided by 2, I believe. .45 amps. And this is positive. So our arrow on the diagram is good. The only one that was negative out of them was IM. That just means this arrow, like the current, is going up instead of down. Okay, nothing to be worried about. Okay, cool. So these would be all of our currents, and they don't agree with the currents here. What I'm real concerned about right here is this is pretty low compared to the other ones, I3, and that's a pretty substantial voltage right here. So that was an 8 volter here on V3. Yeah, so it could be the case that it's just like the voltages were not associated to the proper numbers here. That's my suspicion, but yeah, I would trust my calculations more because I did it step by step and I saw it happen. Okay, so yeah. Currents in the solution are incorrect. And I3 I1 is corresponding to my IL, so that's 3.45. Left. I2 is going up at 1.025. The last one is 3.45 left. Nope, 2.42 to the left. Oh man, last question. That was, time flies when we're having fun, as the old saying goes. So those are all the questions that we have today. If you enjoyed today's Q&A and would like to be notified of when we do this next, please hit the subscribe button and ring the notification bell below. If you're interested in submitting your own questions, please visit the links in the video description. And if you enjoyed today's video, a like would be greatly appreciated. And if you really enjoyed the video, share it with your friends. This has been Millan from OneClass. Today was a great time with the physics. I hope to see you again soon. Take care, stay safe, and have an amazing rest of your day, evening, morning, afternoon, whatever time you're watching this, enjoy yourself. Okay, take care.